Hello, I'm going to give you a whirlwind tour of anyonic quantum computation. So, as you probably know, if you rotate a boson by 2 pi, nothing happens. But if you do the same to a fermion, that gives you a -1 phase. Now, it turns out that due to a quirk of SO2, in 2 dimensions, you can actually have something that's called an anion that picks up a fractional phase upon rotation by 2 pi. Now, one particularly promising anion is the Fibonacci anion, and this occurs in the fractional quantum Hall effect. It turns out that when you rotate a Fibonacci anion, you get a phase of e to the 4 pi I over 5. And you can also think of this as saying it has a fractional spin of 2/5, which is pretty cool. Now, I want to show you how this sort of weird coolness can be translated into quantum computation. So let's talk about anion models in general. Basically, when we fix an experimental setup, we're going to have a range of anions, and each anion is going to have a different charge or flavor. So here's the set of possible charges. And the philosophy to employ here is that any collection of anions is itself another anion with some superposition of charges. This is familiar from the context of spin. If we have 2 spin 1/2 particles, then the collection of the 2 particles together can have total angular momentum 0 or 1. So this is really just a beefed up version of this. So now you have like 2 anions A and B, and they can have a wide range of total charges given by these coefficients here. So you can think of these NCABs as 0 or 1. They usually are. Let's look at an example of this. The Fibonacci anions. So the Fibonacci anion model has 2 types of anions. The first is the trivial charge anion 0, and the second is the non-trivial charge 1. You can think of 0 as basically the vacuum. And what happens when you have vacuum and another particle? What's the total charge of that? Well, it's just the charge of the other particle because the vacuum does nothing. So that explains the first 3 equations here. The last equation is the non-trivial one. It says that the total charge of 2 1 anions can be either 0 or 1. This should remind you of a qubit. Now, because the total charge can have more than one possible value, we call Fibonacci anions non-abelian. This non-abelian nature is extremely important for quantum computation. To understand this, let's think about a collection of more anions. So let's say that I hand you 4 anions, and I tell you their positions, and I tell you that they are 1 anions. Have I told you the full story? Well, absolutely not, because I have not yet described what their collective charges are. To characterize the degree of freedom associated with collective charge, we're going to look for a complete set of commuting observables of total charge. Here is one such CSCO. The CSCO in particular is the total charge of the first 2, the total charge of the first 3, and the total charge of all 4 of them together. It turns out that you can calculate that this is indeed a CSCO. And once you have a CSCO, you also have a eigenbasis. So this labeled graph here describes an eigenbasis of the CSCO. It says that the total charge of the first two anyons is A, of the first three is B, and the first four is C. In more familiar notation, we can write this as a ket. Now, the topological Hilbert space is just the span of these kets. And it turns out that certain restrictions apply on these three numbers due to the fusion rules mentioned earlier for the Fibonacci anyons. And this restricts the dimension of the topological Hilbert space to 5, which incidentally is the 5th Fibonacci number. But this is actually no coincidence, because beautifully, the dimension of the topological Hilbert space for n particles is going to be the n plus 1th Fibonacci number. And this is approximately c times phi to the n for some constant c, and phi the golden ratio. So in light of this, we say that the topological Hilbert space has dimension phi. Now, what's so good about this topological Hilbert space anyway? Well, consider this diagram here. We start with 3 anyons. Now we allow them to loop around each other for a while. And finally, they return to their original positions. What has changed? It turns out the topological Hilbert space characterizes the change. And basically, the change in the topological state is going to depend on the topology of this braid. And why do we like the topological Hilbert space for quantum computation? It's because these actions of braiding are naturally fault tolerant. If you imagine perturbing one of these paths a bit, that will not change the topology, well, usually will not change the topology of the braid, and therefore it does not affect the topological Hilbert space. It remains to be seen how the topology of the braid relates to its action on the topological Hilbert space. To answer this question, let's imagine rotating 2 Fibonacci 1 anyons around each other by 360 degrees. So what happens is actually going to be dependent on the topological space, which is the root of the power of this these anyons for quantum computation. To see this, we can think of these 2 particles as a single particle with a given total charge. And now we can just rotate this big particle like so. Okay. Come on. There we go. So we rotated it. And what does that do? Well, if the total big particle had charge 1, then the effect of this is to place a phase on the system of this number here, which you might recognize from the beginning of this talk. But if the total phase is 0, if the total charge is 0, then rotating a chargeless particle does nothing. So you get no phase. And this is a very important thing to note, because basically this is a Z-gate, except that the phases are a little bit different. And the fact that these phases are not the same is quite important, because if they were the same, then we wouldn't get anywhere with topological quantum computation. But since the phase depends on the topological state, we can do computation with it. And if you want to be real stickler, I'll just note briefly that when we rotated the big particle, we actually also rotated the small particles, so we might want to compensate for that, but that'll just slap an extra global phase on the system. Now let's return to the more general context. Let's think about what happens to the topological Hilbert space when we swap these two these two particles. Well, I claim that it's physically intuitive that this operation doesn't change any of the total charges measured by this CSCO. And that implies that in this basis, this swap is very simple. It just puts a phase on each of the eigenkets, which depends on A. On the other hand, this swap is a little harder to characterize because this swap is not going to commute with this operator here. But we can switch to a new CSCO, which gives us a new basis. And in this new basis, we see that again, because the braiding operation commutes with the CSCO, we again can easily characterize the effect of braiding. And at the end of the day, we can characterize in a similar way the effect of swapping any two adjacent particles. And that gives us a set of n-1 gates that we can apply at will. At this point, we hope that this set of gates is universal on at least a very big portion of our topological Hilbert space. And happily for us, for most anyon models, including the Fibonacci anyon model, this is correct, and we get topological quantum computation, which is universal. Thanks.